Chemical Kinetics Part 5. We're going to take a closer look at differential rate laws and introduce integrated rate laws. Now, in the end of this video, and actually a series of videos to follow, we're going to put together this chart where we have differential rate laws for zero, first, and second order reactions, integrated rate laws for zero, first, and second order reactions, half-life for zero, first, and second order reactions, and then we identify, using the integrated rate law in the slope-intercept line equation form, what straight line graphs would look like and what we can determine from those graphs. This is really a useful document that you would want to have on hand. These are the equations you would want to have on hand when you do kinetics calculations. So why do we call these differential rate laws? Remember that differential rate laws for zero order reactions say that rates equal to K. First order reactions, the differential rate law is that rates equal to K times the concentration of A. And for a second order rate law, rates equal to K times concentration of A squared. And we're assuming we have just a single reactant forming products. We're paying attention to the reactant there. What these all do is they relate rate to concentration. Instantaneous slope on any graph is the slope at any instant on the curve. Now, of course, if you have a straight line, the slope anywhere on the straight line is going to be exactly the same, so the average slope and the instantaneous slope would be the same. If you have a curve, you could graph out the line, just like we have here with our concentration versus time graph. To get the slope at any point on the curve, you could draw a tangent. And let's take a look at this tangent right here that's happening at the very initial point on the curve. We could measure the delta y and the delta x for that tangent. And we could say that the slope of the tangent, wherever it strikes the curve, whatever point it strikes the curve, is the slope of that point on the curve. And that would be the instantaneous slope. And in this case, it's happening right at the start of the reaction, so we'd call that the initial slope. That's the instantaneous slope at the start of the reaction. Now let's assume that we're talking about a single reactant A forming products here. We could say that the initial rate of the reaction is a negative slope at the very start of the reaction. The slope of a concentration versus time graph would be the change in concentration divided by the change in time, and that's the rate of the reaction. But remember that we always want rate to be positive, right? So since this is a downward angling line, we put a negative in front of that slope. So a negative of that negative slope makes our rate positive. So we can say that a negative of the slope at that point is the initial rate of the reaction, and also it's equal to this expression from our differential rate law. This is the rate of the reaction. All right, so let's take a look at, let's expand upon that a little bit and say that our initial rate of reaction, the slope of the tangent at the starting point on a concentration versus time graph, is equal to some rate law expression, K times concentration of A to the m power. Do you really have to graph concentration of A versus time to be able to determine that, to be able to measure that tangent and figure out the slope at that point, at that start of the reaction? Well, the answer is no. Now, what you can do is some calculus. dy divided by dx is known as a derivative in calculus. It's actually a ratio of the differentials. When we say differential, we mean that there's a slight difference there. It's actually an infinitesimal difference in the y values, or an infinitesimal delta y, divided by an infinitesimal delta x. And if you make the delta y infinitesimal and the delta x infinitesimal, we're really talking about the slope at a point or at an instant on the line. So that's instantaneous slope. So there are all different rules about how to calculate derivatives in calculus. And we can say that the initial rate instead of being equal to the slope of the line expressed, or the slope of the point of the initial start of the reaction expressed as the slope of the tangent, we could figure it out as the slope exactly at that point if we could do the derivative in calculus. And remember, that would be equal to whatever our differential rate law expression was. You can calculate the derivative if you know the line equation and you're using calculus. Now, you don't have to know calculus to do kinetics. You can graph it out. You could graph out concentration versus time. You could draw on the tangent point, measure the delta y and the delta x, and you could figure out what the initial rate was that way. But remember that the method of initial rates has to do with this initial slope here, because we're starting with that initial concentration and measuring that rate right at the beginning. We would say the differential rate is equal to a negative slope of concentration versus time, which is that derivative at that point, a negative of that derivative, or a negative of the slope at that tangent to that point. But how does the concentration of A relate to time at any time on the graph? Does that keep going in a straight line if we graph it out? Does it go in a curved line? And if so, how does it curve? Well, I guess we could measure the concentration of A at several times and graph it out and determine that. But here's the question. Is it necessary to graph concentration versus time to be able to make a relationship to concentration versus time at any time? Because you know what? With fast reactions, that would really be a problem. Sometimes reactions happen so fast, like maybe a stick of dynamite, that it would be very, very difficult to measure the concentration of a chemical at any particular point other than that instant when the reaction started. No, we don't have to graph it out. What we can do is we can do some calculus and we can integrate the differential rate laws to find out how concentration relates to time. Remember, the differential rate laws look like this. Now, in the next video, we'll talk about the math behind that integration. You don't necessarily have to be able to do that. You don't have to do calculus. And if you can't do the calculus, then you just have to trust that the equations that we describe as the integrated rate laws are correct.